You know that feeling? A flash of lightning cracks open the sky, or you feel the ground literally shake beneath your feet? It's nature reminding us just how powerful it is. So today, we're going to dig into the science behind two of the most dramatic shows on Earth, lightning and earthquakes. We'll journey from old myths to modern science, and you know the most important part? We'll figure out how to stay safe.
Okay, so here's a wild thought. What's the connection between that little static spark you get from a sweater and a massive sky-splitting bolt of lightning? I know, it sounds kind of out there, but there's a direct link. Stick with me, because by the end of this, you're going to see exactly how these two things are basically the same phenomenon.
You have to imagine, for most of human history, stuff like this was just terrifying, a total mystery, right? There was no science to explain it. So what did people do? They came up with stories, with myths. A lot of the time they figured it had to be angry gods at work. And wow, here they are. Just look at the raw power on display. On one side, you've got the pure electrical fury of a lightning storm, and on the other, the sheer devastation an earthquake can leave behind. These aren't just, weather events. We're talking about incredible releases of energy that can change a landscape and people's lives in a heartbeat. So that quote, that's just one example of the kind of story people came up with to try and make sense of it all. I mean, it's a cool story, right? But the real reason, the actual science, well, as we're about to see, it's all buried deep in the physics and geology of our planet. All right, so let's start up in the sky. If we really want to get a handle on that huge flash of lightning, we've got to zoom way in, all the way back to that tiny spark from your sweater. It all kicks off with something we can't even see. It's called electric charge.
And seriously, believe it or not, the basic idea is the same one that makes your hair stand up when you rub a balloon on it, or that little zap you sometimes get from a doorknob. It is the exact same principle that creates a lightning bolt. The only difference? Scale. A massive scale.
Okay, so here's the one really important rule of physics you need to remember. It's kind of like magnets. If charges are the same, say two positives or two negatives, they push each other away. They repel. But if they're different, an opposite charge, they pull towards each other. They attract. This one simple idea, it's the key to all of this.
And you can see it happening right here, plain as day. You've got two balloons, they're both rubbed with the same cloth, so they get the same charge. And look, they're actively pushing each other apart. But then, you bring in something with the opposite charge, and boom, they pull right together. Repel and attract. It really is that simple. So let's just put a formal name on this. Scientists call these things electric charges, and just by convention, we label them positive and negative. And really, here's the main takeaway. Every single spark, every bit of electricity, every lightning bolt, it's all just these two charges moving around trying to find a balance. Okay, now let's take that simple idea and scale it way up. Think about what's going on inside a giant thunderstorm cloud. It's this incredibly violent mix of churning air and water and ice particles. All that friction, it's like rubbing a billion balloons at once. And what it does is separate the charges. You get a huge buildup of positive charges way up at the top of the cloud and a whole bunch of negative charges gathering at the bottom.
Sooner or later, that separation of charges just gets to be too much. The tension is huge. The air itself just can't keep them apart anymore. And those negative charges at the bottom of the cloud are just desperate to connect with the positive charges on the ground below. When they finally make that connection, bam, you get this massive, sudden flow of energy to balance things out. That's an electric discharge. And what do we see? A brilliant flash of lightning. And what do we hear? A huge roar of thunder.
So, there you have it. Lightning is basically a huge release of built-up electrical energy in the sky. Pretty cool, right? But now, let's shift our focus. Let's go from the atmosphere down to the solid ground beneath our feet, because there's a different kind of built-up energy down there, and its release causes another one of nature's most powerful events, the earthquake. So when you feel the ground shaking, it's easy to think it's happening right there on the surface. But that's not where it begins. The real origin point is a disturbance deep inside the Earth's uppermost layer, this, relatively thin shell that we live on, called the crust. And this is the key to understanding everything. The Earth's crust isn't one solid piece, like an eggshell, not at all. It's actually broken up into these massive continent-sized slabs that we call tectonic plates. And here's the thing, they are never still. They're in this constant, super slow-motion dance, always grinding against each other, pushing and sliding past. So, what happens when these giant plates are on the move?
Well, sometimes they crash right into each other, and one is forced to slide underneath the other one. Other times they just scrape past each other side by side. Either way, these movements build up a huge amount of stress in the rock. And when that stress finally gets to a breaking point and is suddenly released, boom, it sends out massive shockwaves. And that's what we feel as an earthquake.
So it totally makes sense, right? Since all the action is happening where the plates meet, those boundaries are the weakest spots in the crust. We call these areas seismic zones or fault zones, and that is where, by far, the vast majority of all the world's earthquakes happen. Now, we measure how powerful an earthquake is on something called the Richter scale, but here's something you really got to understand about it. It's not a simple 1, 2, 3 scale. It's logarithmic. That means each whole number is 10 times more powerful than the number before it. So a magnitude 7 quake isn't just a little bit worse than a 6. It is 10 times more intense. To put that in perspective, those devastating earthquakes in Bhuj and Kashmir, they were both over a 7.5. That is just a staggering, unbelievable amount of energy. Okay, so understanding the science behind all this is a huge step, right? It takes us from being afraid of some big mystery to actually having knowledge. But knowledge is only half the battle. So now, let's use what we know to talk about what to actually do. Let's learn how to stay safe.
All right, so let's say you're caught outside in a lightning storm. What do? These steps are absolutely critical. First, get away from anything tall. Trees, light poles, anything like that. There are lightning magnets. Second, do not lie flat on the ground. Instead, you want to make yourself the smallest possible target. You squat down low, just like this, with your head tucked in.
Okay, being inside is definitely safer, but you're not totally in the clear. You still have to be careful. Lightning can travel through a building's plumbing and its electrical wiring, so that means no showers or baths during the storm. Stay off any corded, landline phones, and don't touch metal pipes. It's also a really good idea to unplug big things like your computer or TV to protect them from a power surge.
Now for an earthquake. If you're at home when one hits, there's a simple mantra to remember. Drop, cover, and hold on. That means drop to the ground, get under something sturdy, like a heavy table, and hold on until the shaking stops. And make sure you stay away from anything tall and heavy that could fall over, like a bookshelf. Oh, and if you happen to be in bed, just stay put and cover your head with a pillow.
And what if you're outdoors? Your number one job is to get to a clear, open spot. You need to get away from buildings, trees, and especially overhead power lines. Anything that could fall on you. Now, here's a surprising one. If you're in a car or a bus, stay inside. It's actually a pretty safe place to be. Just have the driver slow down and pull over to a clear spot, well away from bridges and overpasses, and just wait it out. So, just think about the journey we've just taken. We went from ancient myths about bulls holding up the earth to the actual science of plate tectonics. We've gone from being terrified of angry gods in the sky to understanding electric discharge. See, knowledge, it gives us the power not just to understand the world around us, but to protect ourselves from its biggest forces. So the real question left is, how are we going to use that knowledge to build a safer world?